Welcome to this video lecture. This is Mark Scythian. The date today is August 9th, 2018. This will be another applied calculus modeling video lecture focusing on human population growth and forecasting. So here we have the governmental statistics of human global population figures between the years 1900 and 2018. So the population on Earth has been recorded to go from 1.5 billion people globally in 1900 to 7.5 billion people globally in 2018, the start of 2018. So these are all of the compiled governmental statistics on Earth published to a consensus on the global population figures. So we're assuming this is correct. And from that statistic, we can then use applied calculus power and exponential functions to predict the population forecast into the future based on this statistic. So a good question to ask is find out what year human global population will reach 8.6 billion people based on the population increase rate of change between the years 1900 and 2018. So the first thing we need to do is establish a finite non-continuous power function, ab to the t power. And then we need to establish the time limitations for a finite power function. So t equals 0 would denote 1900. T is equal to 118 years after 1900 or 2018. So then we can use the factor, which is established as a growth factor, not a decay factor. So the factor will obviously be above 1. So we take 7.5 billion. We'll just use 7.5 times b. So we'll just take the coefficient out of that times a billion. So 7.5 divided into 1.5 billion would equal t to the 118th power. So in order to find out the growth factor, we have to take the 118th root, or the 1 over 118 power of this ratio. So when we do so, we get a growth factor of this value here, 1.01373, 2744. Now we can establish a finite power function based on what we do know. So we would write the initial value of 1.5 billion, parentheses, the growth factor to the t power. And then our finite limit is between t is equal to or greater than 0, equal to less than 118. So we are limited we can put t in only between 0 and 118 to get the population growth, but we can find this out between the known years of 1900 and 2018. But in order to do a forecast based on what we do know, this reliable growth that's recorded, of course, every year it's a different rate of change. It's not linear either, but we are able to create a mathematical model on what we do know that is accurate. But to go past 2018, we would not have an accurate mathematical model unless we converted it into an infinite or continuous exponential to the kt power to do forecasting past the time limits. So in order to do that, we would take the natural logarithm, the ln, of the growth factor. So we do that, we get this value here. Then we set up, so we know the constant, the k. That would be this value here. So we create an infinite or continuous exponential function to mathematically model a continuous projected forecast based off this power function. So when we do so, we get 1.5 initial value e exponential function to the constant times t. So here is the accurate mathematical equation governing the population increase on Earth. So this is what we have to create here because it is continuous function. So now all we have to do is enter in a projected forecast or a targeted population number, which is obviously happening in the future. Question is, find out what year the human population will reach 8.6 billion people. So if we're in 2018, we're still somewhere around this number. What we want to know is the year when that will happen. So we can equal the y function, 8.6, the output, and then the input would be, of course, this equation model here. So now all we have to do is use the rules of mathematics and solve for t, the t power. So k t power exponential function to equal 8.6. So we'd have to divide both sides by 1.5 to isolate the e. Then to get rid of the e, we'd have to multiply the e times the natural log. So we have to do that on both sides. And then we can continue on and get the natural log of this ratio, which is this function, this value here. 8.6 divided into 1.5, that would be this 5.733. We get the natural log of that divided into this k here because we've eliminated the e by multiplying both sides by natural log. So we're left with an algebraic expression. So when you take the natural log of this constant divided into the k, or the natural log of the ratio divided into the k, then you will get the t, 128. So t equals 0, 1900. So t equal 128 is 1900 plus 128, so 2028. In the year 2028, global human population will reach 8.6 billion people. Now, another question to really ask that's important is at what rate of change in terms of population increase per year was the human global population changing in the years 1900, 1950, 2000, and 2017? And then also, what about 2027, right before we reach 8.6 billion people on Earth? You have to take this equation, which models population growth on a continuous function. You have to work with this. So we copy that down again. This is the mathematical model which represents continuous population growth. So we first have to check the exponential modeling equation representing human population increase as a continuous function as being accurate. So we will enter in the start year of 1900, which is t equals 0, into t. So on your calculator, you would hit 1.5 and then the shift key for the exponential function. It should be on the shift of the natural log, and then up, it'll instantly go to an exponential symbol, and then you enter in this constant, then multiplication times 0 for year 1900. T is equal to 0. Of course, you get 1.5 again, because this becomes 1 times billion. T equals 0 is 1900, so correct. And then we check the upper limit, 118, which is 2018, year 2018. Also, we get 7.5 times 1 billion, and that's correct too. So this equation here is correct. Equation verified is correct. So now we can use the rules on calculus for differentiating exponential functions. So as you know, f of x, if it was to equal the exponential function to the x power, if we were going to get f prime, or the derivative of this, it would also be x e to the x in the rules of calculus. So that being said, all we have to do is, if we were going to take the derivative, or we had to take the integral or the reverse, we would also use those functions that reverse it back to the function. So you'd always take that coefficient and multiply it times the coefficient before the e, and then repeat the whole ex. So here's the same equation up here. To get f prime or p prime, the derivative, we would just take this. When you get the derivative of single degree expression, you would just take the coefficient out of that. So if it was 5x, the derivative would be 5, becomes a constant. So this one, we just take this coefficient, the k, and we multiply it times this base here. And then we repeat this whole equation again. So when we compute it, we get this coefficient to the exponential, and then we repeat the kt again. So this would be the derivative of this equation, for which when we put the time in, we will know the exact rate of change in population growth per year in any year we put in for t. That is assuming the original information here about global population statistics is accurate and reflects the actual population record of the Earth. So now, using this derivative of the mathematical model of population growth, we can enter in the year and know the rate of change in that given year. Of course, this is increasing. So every year, it's not going to be a constant increase in population. In 1900, it might be so many people per year. And 1905, it might be not the same number. It might be increasing. It may have a the rate of change that's not the same, but still increasing. So now we've got the derivative of the function, and we can figure out that information. So original question, at what rate of change in terms of population increase per year was the human global population changing in these years, 1900, so t is equal to 0, t is equal to 50, t is equal to 100, t is equal to 117, and then 127, because we want it right before 2028. So we go ahead and enter in those t values for whatever year. So 1900, that would be t to the 0. We get 0.2046 times a billion. So in 1900, there was 20.46 million people per year increase in 1900. Then in 1950, t is equal to 50. Same computation, except we put 50 in for t. We calculate 40.46 million people increasing per year in 1950. Then in year 2000, same application, except t is equal to 100. We have 80 million people increasing per year in the year 2000. Then in the year 2017, which would be what, last year, we put 117 in, and we get 101 million people per year. And then, of course, we want to know what the population increase will be in 2027 in that year, per year. Again, 127. That t should be 127. I entered that in. So I got 0.1156 billion. So that's 115.7 million people per year increase in 2027. So that answers some very important questions, but if you wanted to take it further and find out what it would be in 2028, you could put in t. It would be 128 for the t to find that in billions population increase per year during that year. So that would be the increase or the rate of change per the x function or the time function. So the x-axis is the time, and so we're representing it by t here. So, but you have to get the derivative of this mathematical model to know the rate of change. Now, if you get the integral of this function, you would reverse it and it would become the original function again. And then this one would just tell you the population, what it is by the year, or even the decimals of the year. Like 118.5 would be June of 2018, right? And you can get that model and it would be pretty accurate to what is listed in the population or the census for the world. And but if you wanted to use this beyond what is known from 2018, it's a continuous function. And of course, there is a limit to the equation. It will fail eventually because there will be peak population. And that's actually the second derivative. You get another derivative of this, and this is what they call the inflection point. These will be the critical point where the population rate is highest in increase per that given time, but it's still increasing by the function of time. But there would eventually be a cutoff point, a peak point in the population. Something happens on the Earth, and then that would have to factor in other environmental factors with mathematical modeling, then intertwined with these equations into an algorithm. But many population or mathematical modelers or finite elemental analysts doing analyses are looking at this number, 8.6 billion, perhaps as being peak population, although it is only known at this point in time. Who's to say a new technology comes out or new discoveries that don't cause that to happen. But at this point in time, for what is known, that is kind of the number they're looking at now, is 8.6 billion people would be where this rate of change would stop accelerating upward, and then it would either stay level or decrease. So they call that the inflection point on the graph. So that would be the second derivative. And you can, again, get the derivative of this constant, do the same process here, and then you can equal the p to 0, second prime, and then get the t. And but that does require a additional information that then goes back into the statistics. So that could actually be figured out. Let's say 2021, they publish a rate of change or demographic. So we would put t is equal to 0 for 2018 and take it to, let's say, 2021. And then we have a different rate of change modeling, which then may not just supersede, but could also be integrated into an algorithm with this one. And then you can go to the second derivative and find the inflection point, and then the rates of change are different. And then it really tells you if 8.6 billion is the peak population. But right now, as of now, from that type of modeling, 8.6 is the forecasted peak population. Not necessarily, only now, but it could change. It could keep going up, and sustainability would be there. But at this point, 8.6 b is pretty much the inflection point. So once you get the second derivative of this first derivative, and then you equal the p to 0, you can get the time at which the population will reach a peak and then taper off or remain steady. So that requires a few more statistics extra that are recorded from reality, and then you can go to the second derivative to figure that out. But for face value, we know that the actual figures are right now in 2017, or I'm sorry, 2018. What did I say? I only went up to 2017, but you'd have to put T is 118. But we're right about, let's say last year, we were about 101 million people per year increase in population globally. So this is another very helpful tool in calculus, the power and exponential modeling functions. And then you can then derive or integrate them for whatever specific information you need to occur in the future, finding out unknown information from known information. So thanks for watching this video and have a great day.